Hello everyone, myself Sagar and I am going to present a seminar on eCOS and tinyOS. So now let us look at what is eCOS. The Embedded Configurable Operating System is an open source royalty-free real-time operating system intended for embedded applications. The system is targeted at high-performance small embedded systems. For such systems, an embedded form of Linux or other commercial operating system would not provide the streamlined software required. The eCOS software has been implemented on a wide variety of processor platforms, including Intel IA32, PowerPC, Spark, ARM, etc. It is one of the most widely used embedded operating system. It is implemented in C and C++. Okay, now let us look at what are eCOS configuration tools. An embedded operating system that is flexible enough to use in a wide variety of embedded applications and on a wide variety of embedded platforms must provide more functionality than will be needed for any particular applications and platforms. So, for example, many real-time operating systems support switch tasking, concurrency control, and a variety of priority scheduling mechanisms. A relatively simple embedded system would not need all these features. The challenges is to provide an efficient user-friendly mechanism for configuring selected components and for enabling and disabling particular features within the components. So the eCOS configuration tools, which runs on the Windows or Linux, is used to configure an eCOS package to run on a target embedded system. The complete eCOS package is structured logically. So it makes it easy using the configuration tool to assemble a target configuration. At a top level, eCOS consists of number of components and the configuration user may select only those components needed for the target application. For example, a system might have a particular serial input-output device. So at the top level, eCOS consists of number of components and the configuration user may select one of these components needed for target application. So for example, a system might have particular serial input-output device. The configuration user would select serial input-output for his configuration. Then select one or more specific input-output device to be supported. The configuration tool would include the minimum necessary software for that support. So the configuration user can also select specific parameters such as default data rate and the size of input-output buffers that can be used. This configuration process can be extended down to the finer level of details, even to the level of individual lines of code. Say for example, the configuration tool provides the option of including or omitting priority inheritance protocol. So this figure shows the top level of the eCOS configuration tool as seen by the tool user. Each of these items on the list in the left hand window can be selected or deselected. When an item is highlighted, the left hand window provides the description and the upper right hand window provides the link to the further documentation plus additional information about the highlighted items. Items on the list can be expanded to provide a finer grained menu of options. Here you can see the menu of options. So the next figure shows the typical example. the overall process for creating the binary image to execute the embedded system. This process is on the source system such as Windows or Linux. The process is run on the source system such as Windows or Linux platform, and the executable image is distinct to execute on the target embedded system such as sensor in the industrial environment. So at the highest software level is the application source code for the particular embedded application. This code is independent of eCOS but makes the application program interface, that is APIs, to sit on the top of the eCOS software. There may be only one version of the application source code, or there may be variations for different versions of the target embedded platforms. In this example, the GNU makes utility that is used to selectively determine which pieces of the program need to be compiled or recompiled in the case of the modified version of the source code, and issues the command to recompile them. The GNU cross compiler executing on the source platform that generates the binary executable code for the target embedded platform. The GNU linker links the application object code with the code generated by the eCOS configuration tool. The later set of the software includes the selected portions of the eCOS kernel plus the selected software for the target embedded system. The result can be loaded into the targeted system. So this is the diagram for loading an eCOS configuration. Here you can see GNU makes utility sent to the application source code. So once the source code of the application is done, the GNU cross compiler will passes the control to the GNU linker. The GNU linker will check the eCOS kernel library and then loads the eCOS configuration into the executable file. So coming to the eCOS components. A key design for the requirement for eCOS is portability to different architecture and platforms with minimal effort. To meet this requirement, eCOS consists of a layered set of components, which you can see in this slide. So coming to the parts of the eCOS layered structure. Hardware abstraction layer. It is the bottom most part of the eCOS layered structure. So at the bottom is the hardware abstraction layer, that is HAL. The HAL is the software that presents a consistent API to the upper layer and maps the upper layer operations onto the specific hardware platform. Thus the HAL is different for each hardware platform. So this is the example that demonstrate how the HAL abstract hardware specific implementation for same API calls on two different platforms. As this example shows, the call from the upper layer to the enable interrupt is same on both platforms, but the C code implementation of the function is specific to each form. The HAL is implemented in three separate modules. That is architecture, variant and platform. Architecture. So architecture defines the processor family type. This module contains the code necessary for the processor startup, interrupt delivery, context switching and other functionality specific to the instruction set architecture of that processor family. So coming to the variant. Variant supports the features of the specific processor in the family. An example of supported feature is an on-chip module such as memory management unit. So one more module of the HAL is platform. Platform that extends the HAL support to tightly coupled peripherals like interrupt controllers and timer devices. This module defines the platform or board that includes the selected processor architecture and variant. It includes code for startup, chip selection configuration, interrupt controllers and timer devices. So we have to note that HAL interface can be directly used by any of the upper layer, promoting efficient code. So coming to the eCOS kernel design. eCOS kernel was designed to satisfy four main objectives. They are low interrupt latency, low task switching latency, small memory footprint, deterministic behavior. So coming to the low interrupt latency, the time it takes to respond to an interrupt and begin executing an ISR is low interrupt latency. And now we'll see what low task switching latency means. The time it takes from when a thread becomes available to when actual execution begins. This is the low task switching latency. Now coming to the small memory footprint, memory resources for both program and data are kept to be minimum for allowing all components to configure memory as needed. So coming to the deterministic behavior, throughout all aspects of execution, the kernel performance must be predictable and bounded to meet real-time application requirements. The eCOS kernel provides the core functionality needed for developing the multi-threaded applications. The core functionalities are the ability to create new threads in the system, either during startup or when the system is already running. Control over the various threads in the system, for example, manipulating their priorities. And the third one is a choice of schedulers determining which thread should be currently running. And the fourth one is a range of synchronization primitives allowing threads to interact and share data safely. The last one is integration with the system's support for interrupts and exceptions. So some functionalities that is typically included in kernel of an operating system is not included in eCOS kernel. Now let us see what is not included in eCOS kernel. For example, memory allocation. Memory allocation is handled by the separate package. Similarly, each device driver is a separate package. Various packages are combined and configured using the eCOS configuration technology to meet the requirements of application. This makes for a lean kernel. Further, the minimal nature of the kernel means that for some embedded platforms, the eCOS kernel is not used at all. Simple single-threaded applications can be run directly on HAL. Such configurations can incorporate needed C library functions and device drivers, but avoid the space and time overhead of the kernel. There are two separate techniques for utilizing kernel functions in eCOS. One way to employ kernel functionality is by using C API of kernel. Examples of such are CGY thread create and CGY underscore mutex underscore lock. These functions can be invoked directly from the application code. On the other hand, kernel functions can also be invoked by using compatibility packages that allow application code to POSIX thread. The compatibility packages allow application call to stand on standard functions like pthread underscore create and those functions are implemented using the basic functions provided by the eCOS kernel. Code sharing and reusability of already developed code is easily achieved by use of compatibility packages. So coming to the eCOS input-output systems. The eCOS input-output system is a framework for supporting device drivers. A variety of drivers for the variety of platforms are provided in the eCOS configuration packages. These include drivers for serial devices, Ethernet, flash memory interface, and various input-output interconnections such as PCI, that is Peripheral Component Interconnect, and USB, that is Universal Serial Bus. In addition, user can develop their own device drivers. So the basic principal objective for the input-output system is efficiency. With no necessary software layering or extraneous functionality. Device driver provides the unnecessary functions for input-output buffering and device control. As mentioned, device drivers and other high-layer software may be implemented directly on the HAL. If this is appropriate, if specialized kernel type functions are needed, then the device driver is implemented using the kernel APIs. The kernel provides a 3-level interrupt mode. They are interrupt service routines, ISR. These are invoked in response to the hardware interrupt. Hardware interrupts are delivered with minimal intervention to an ISR. The HAL decodes the hardware source of the interrupt and calls the ISR of the attached interrupt object. The ISR may manipulate the hardware, but it is only allowed to make restricted set of calls on the driver APIs. When it returns an ISR may request that its DSR should be scheduled to run. So next level of the interrupt model is deferred service routines, that is DSR. Invoked in response to a request by an ISR. A DSR will be run when it is safe to do so without interfering with the scheduler. Most of the time the DSR will run automatically after the ISR, but if the current thread is in the scheduler, it will be delayed until the thread is finished. A DSR is allowed to make a larger set of driver API calls, including in particular being able to call CYG underscore DRV underscore condition underscore signal to wake up waiting threads. So coming to the third level of the interrupt module, that is threads. The threads are the clients of the driver. Threads are able to make all API calls and in particular are allowed to wait on mutexes and condition variables. So basically the principal objective is efficiency with no necessary software layering. Now coming to the eCOS scheduler. The eCOS kernel can be configured to provide one of two scheduler designs, the bitmap scheduler and a multi-level queue scheduler. The configuration user selects the appropriate scheduler for the environment and the application. The bitmap scheduler provides the efficient scheduling for a system with a small number of threads that may be active at any point in time. The multi-queue scheduler is appropriate if the number of threads is dynamic or if the desirable to have multiple threads at the same priority level. The multi-level scheduler is also needed if the time sizing is desired. So coming to the bitmap scheduler. A bitmap scheduler supports a multiple priority level. but only one thread can exist at each priority level at a given time. Scheduler decisions are quite simple with this scheduler. When a blocked thread becomes ready to run, it may preempt a thread of lowest priority. When a running thread suspends, the ready thread with the highest priority is dispatched. A thread can be suspended because it is blocked on the synchronization primitive, because it is interrupted, or because it relinquishes the control. Because there is only one thread at most at each priority level, the scheduler does not have to make decision as to which thread at the given priority level should be dispatched next. So the bitmap scheduler is configured with 8, 16 or 32 priority levels. A simple bitmap is kept at the thread that are ready to execute. The scheduler needs only determine the position of the most significant 1 bit in the bitmap to make a scheduling decisions. So coming to the multi-level queue scheduler priorities. As with the bitmap scheduler, the multi-level queue scheduler supports up to 30 level priority levels. The multi-level queue scheduler allows the multiple active threads at the priority level, limited only by system resources. This figure illustrates the nature of the multi-level queue scheduler. A data structure represents the number of ready threads at each priority level. When a blocked thread becomes ready to run, it may preempt a thread of lower priority. As with the bitmap scheduler, a running thread may be blocked on a synchronization primitive because it is interrupted or because it relinquishes control. When a thread is blocked, the scheduler must first determine if one or more threads at the same priority level as the blocked thread is ready. If so, the scheduler chooses that one of the front of the queue. Otherwise, the scheduler looks for the next highest priority level with one or more ready threads and dispatch one of these threads. In addition, the multi-level queue scheduler can be configured for the time slicing. Thus, if the thread is running and there is one or more ready threads at the same priority level, the scheduler will suspend the running threads after one time slice and chooses the next thread in the queue at the priority level. This is a round-robin policy with one priority level. Not all applications require time slicing. For example, an application may contain only thread that block regularly for some other reason. For this application, the user can disable time slicing. Which reduces the overhead associated with timer interrupts. Now coming to eCOS thread synchronization. The eCOS kernel can be configured to include one or more of 6 different thread synchronization mechanisms. These include the classic synchronization mechanisms, that is mutex, semaphores and condition variables. In addition, eCOS supports 2 synchronization mechanisms that are common in real-time system, namely event flags and mailboxes. Finally, eCOS kernel supports spin lock, which is useful in symmetric multiprocessing systems. So coming to the mutexes. The mutex was introduced in chapter 6. Recall that mutex is used in enforce mutually exclusive access to the resource, allowing only one thread at a time to gain access. The mutex has only 2 states, that is locked and unlocked state. This is similar to the binary semaphore. When the mutex is locked by one thread at any other and other thread attempting to lock the mutex is blocked. When the mutex is unlocked, then one of the thread blocked in the mutex is unblocked and allowed to lock the mutex and gain access to the resources. The mutex differ from a binary semaphore in two aspects. First, the thread that locks the mutex must be in one to unlock it. In contrast, it is possible for one thread to lock a binary semaphore and to go another for unlock it. The other difference is that mutex provide protection against priority inversion, whereas a semaphore does not. The eCOS kernel can be configured to support either priority inheritance protocol or a priority ceiling protocols. So coming to mutex condition variables. A condition variable is used to block a thread until a particular condition is true. Condition variables are used with mutexes to allow multiple threads to access shared data. They can be used to implement monitors. The basic commands are cyg underscore condition underscore wait. So this causes the current thread to wait on a specified condition variable and simultaneously unlocks the mutex attached to the condition variable. cyg underscore condition underscore signal wakes up one of the thread waiting on this condition variable, causes the thread to become the owner of the mutex. So these condition variables are used with the mutex to allow multiple threads to access shared data. In eCOS, condition variables are typically used in conjunction with mutexes to implement the long-term waits for some condition to become true. Now we will go into the tinyOS. The eCOS system provides a more streamlined approach for an embedded OS than one based on the commercial general purpose OS, such as an embedded version of the Linux. The eCOS and similar systems are better suited for small embedded systems with tight requirements on memory, processing time, real-time response, power consumption and so on. So the tinyOS takes the process of streamlining to much further point, resulting in a very minimal operating system for embedded system. The core operating system requires 400 bytes of code and data memory obtained. tinyOS represents a significant departure from other embedded operating systems. One striking difference is that tinyOS is not a real-time operating system. The reason for this is expected workload, which is in the context of a wireless sensor network, as described in the next subsection. Because of the power consumption, these devices are off most of the time. Applications tend to be simple with the processor contention. Not much is an issue. So coming to the wireless sensor network. This is the diagram for the typical wireless sensor network topology. tinyOS was developed primarily for use with network of small wireless sensors. A number of trends have enabled the development of extreme compact lower power sensors. The well-known Moore's law continues to drive down the size of the memory and processing logic elements. Smaller size in turn reduces power consumption. Low power and small size trends are also evident in wireless communication hardware. As a result, it is possible to develop an entire sensor complete with a logic in a cubic millimeter. The application and system software must be compact enough that sensing, communication and computation capabilities can be incorporated in a complete but tiny architecture. Low cost, small size, low power consuming wireless sensors can be used in a host applications. So this figure shows a typical configuration. A base station connects the sensor network to the host PC and passes on the sensor data from the network to the host PC, which can do data analysis or transmit the data over a corporate network or internet to an analysis server. Individual sensors collect data and transmit these to the base station, either directly or through sensors that act as a data relays. Routing functionalities is needed to determine how to relay the data through the sensor network to the base station points out that in many applications, the user will want to be able to quickly deploy a large number of low-cost devices without having to configure or manage them. This means that they must be capable of assembling themselves into an ad hoc network. The mobility of individual sensors and presence of RF interference means that the network will have the capability of reconfiguring itself in a matter of seconds. So now coming to the tinyOS goals. With the tiny distributed sensor application in mind, the following goals were set for tinyOS. That is, allow high concurrency. In typical wireless sensor network application, the devices are concurrently insensitive. Several different flows of data must be kept moving simultaneously while sensor data are input in a steady stream. Processed result must be transmitted in a steady stream. In addition, external controls from remote sensors or base stations must be managed. So the second goal is operate with limited resources. The target platform for tinyOS will have limited memory and conceptual resources and run on batteries or solar power. A single platform may only offer in kilobytes of program memory and hundreds of bytes of RAM. The software must make efficient use of the available processor and memory resources while enabling low power consumption. So the third goal is adapt to hardware evolution. Most hardware is in constant evolution. Applications and most system services must be portable across hardware generations. Thus, it should be possible to upgrade the hardware with little or no software change if the functionality is the same. And the fourth goal is support a wide range of applications. Applications exhibit a wide range of requirements in terms of lifetime communication, sensing and so on. And the fifth goal is support a diverse set of platforms. As with the preceding point, a general purpose embedded operating system is desirable. So the last goal is be robust. Once deployed, a sensor network must run unattended for months or years. Ideally, there should be redundancy both within a single system and across the network of the system. Now coming to the tinyOS components. Embedded software system built with the tiny operating system consists of set of modules called components. So the different components of the tiny operating system are single hop networking, ad hoc routing, power management, times, non-violating storage control. So all the components in the tinyOS operating system have the same structure. An example of this will be shown in this figure. The shaded box in the diagram indicates the component which is treated as an object that can be accessed by the defined interface indicated by the white box. The component may be hardware or software. Software components are implemented in C, which is an extension of C with two distinct features: a programming model which component interacts via interface. Architecture consists of the layered arrangement of components. Each component can link to only two other components, one below it in the hierarchy and one above it. A component issues command to its lower level component and receives event signal from it. Similarly, the component accepts command from its upper level. So the component and issue event signals to it. At the bottom of the hierarchy and hardware component, and at the top of the hierarchy are application components, which may not be part of the standardized tinyOS suite, but which most conform to the tinyOS component system. A software component implements one or more tasks. Each task in a component is similar to the thread in an ordinary operating system with certain limitations. So the components are organized into the configuration by wiring them together, and their interfacing are equating the interface of an configuration with some of the interfaces of the components. A simple example is shown in this figure. The uppercase C stands for components. Uppercase C stands for components. It is used to distinguish between the interface, that is the timer, and the component that provides the interface, that is the timer C. The uppercase M stands for module. The naming convention is used when the single logical component has both a configuration and a module. The timer C components providing the timer interface is a configuration that links to implement to clock and LED providers. So now coming to the tinyOS scheduler. The tinyOS scheduler operates across all components. Virtually all embedded systems using tinyOS will be uniprocessor systems. Only one task executes at one time. A default scheduler is in tinyOS is a simple first in first out queue. A task is posted to the scheduler either as a result of an event which triggers the position, or as a result the specific request by running task to schedule another task. The scheduler is a power aware. This means that the scheduler puts the processor to sleep when there is no task in the queue. The peripherals remain operating so that one of them can wake up the system by means of a hardware event signal to the lowest level component. Once the queue is empty, another task will be scheduled only as a result of direct hardware event. Now coming to the example of tinyOS application, that is search. So this figure shows the configuration assembled from the software and hardware components. This simplified example called search describes in performs periodic sensor samplings and use ad hoc multi-hop routing over the wireless network to deliver the sample to the base station. The upper part of the figure shows the components of the search, that is represented in the boxes, and the interface by which they are wired, that is represented by the arrow lines. The SearchM component is the application level component that operates on the configuration. So now coming to the next portion. This shows the configuration of the search application. This example will illustrate the strength of the tiny operating system approach. The software is organized as an interconnected set of simple modules, each of which defines one or few tasks. Components have simple standardized interface to the other component, but they have hardware or software. Thus, the components can be easily replaced. Components can be hardware or software with the boundary change not visible to the application programmer. tinyOS resource interface. tinyOS provides the simple but powerful set of conventional for dealing with the resources. There are three types of resources, that is dedicated, a resource that a subsystem needs exclusive access to it all times, and the next one is virtualized. Every client of the virtualized resource interacts with it as if they were dedicated resources, with all virtualized instances being multiplexed on the top of single underlying resources. The next one is shared. The shared resources abstraction provides access to the dedicated resources to an arbiter component. This is the shared diagram of the shared resource configuration. This simplified view of the shared resource configuration is used to provide access to the underlying resources associated with each resources to be shared in an arbitrary component. The arbiter enforces a policy that enables a client to look the resources used it and then release the resources. The shared resource configuration provides the following interface to the client. The first one is resource, and the second one is resource requested, and the third one is resource configured. The last one is resource specific interface. In addition to the dedicated resources, the shared resource configuration consists of two components. The arbiter accepts request for access and configuration from a client and enforces lock and underlying resources. The shared resource component mediates the data exchange between the client and underlying resources. Arbitrary information passes the arbiter to the shared resource component controls the access of the client to the underlying resources. Thank you.